We're going to get introduced to the unit circle, and the unit circle is also going to get us the three big ideas of this unit. Now you might think, what the heck? We're doing trigonometry? How does this relate to circles? Well, we're going to see how trigonometry is related to circles, in particular the unit circle. And the unit circle is a circle that's right at the origin here with a radius of 1. Okay? Now, if you make a radius anywhere on the circle, you could draw a line back to the nearest x-axis, which would cause you to make a reference angle. It doesn't matter where that radius would be. Right now it's in quadrant 1, and in fact my reference angle is exactly the same as my actual angle theta. And in that circle, you could say, if I picked any point, well, it would have an x-coordinate and a y-coordinate. The x-coordinate would obviously be along the x-axis, the y-coordinate would be the height here of that triangle, and I went straight down, so it makes a right-angled triangle. And you already know a squared plus b squared equals c squared from the past. What you just did with a squared plus b squared equals c squared is you have created the equation of the unit circle, which is right here. Right? That's the equation of the unit circle. In fact, if you change the radius, you could do a squared plus b squared equals c squared and find the equation of any circle you want. Which is kind of cool, because you know equations of lines, you know equations of parabolas. This is the equation of a circle. The equation of a circle is just a squared plus b squared equals c squared. X squared plus y squared equals 1 squared. Now, here I'll take out my highlighter, highlight that's unit circle. Now on that, if you think about trigonometry, you know what sine of theta and cos of theta and tan of theta are. Because you remember SOHCAHTOA from grade 9 and 10. So if I wanted to write out what's sine of theta, I would go to my triangle and look, what's the opposite side? It's y. What's the hypotenuse? It's 1. Sine of theta is just y. And if I do cos of theta, it's the adjacent side over the hypotenuse, which is just x. And this is actually, we're going to write these three big ideas on the next page, that instead of labeling points on the unit circle as x comma y, we can now describe them as the x-coordinate is always cos of theta, and the y-coordinate is always sine of theta. So I think you have space on page 470. So 470 at the bottom of the page. You can highlight it that we just discovered big idea for a number 1. For the unit circle, on the unit circle, points can be labeled using theta instead of x and y. The x-coordinate is cos of theta. The y-coordinate is sine of theta. Big idea number 2. The equation of the unit circle is x squared plus y squared equals 1. So, since x is cos and y is sine, I can replace x with cos theta and y with sine theta, and then I get my x squared plus y squared equals 1 becomes cos squared theta plus sine squared theta equals 1. Here's a notation thing that you can lose an E3 error on, and it's the first time that you're probably seeing it. When we decide to take cos theta and square it, mathematicians don't like brackets because it seems like it's unsimplified when you have brackets. So they're like, I don't always want to write brackets when I write cos squared. But then it became a problem because if I take away the brackets and just write this, now it's not clear. One mathematician might look at that and say, is everything squared? Or is just the theta squared? Like, is this happening, the first thing, or is this happening, the second thing? And mathematicians also don't like it when things are unclear. So a decision was made. If we want the whole thing to be squared, we write the squared after the cos or after the sine and write the theta afterwards. If we just wanted the theta to be squared, we could write it like, writing it like this means the theta is squared. And that avoids brackets in both situations. So if you write the squared after the whole thing, that would be considered an E3 error. So that's big idea number 2. That if you choose any angle, if the angle theta has to be the same, I'm going to pull up a calculator right now. And we're going to do some math. Here's my calculator. We're going to do some mental math. First of all, I'm going to get you, let's do, it's the 15th. Let's do 15. If you do cos of 15, there it is. How would you have got that to 8 decimal places? And then I'm going to square it. All right, would you have got that to 8 decimal places? Now I'm going to do sine of 15. Same thing, and I'm going to square it. Now apparently, if I take the cos squared answer and I add the sine squared answer, it comes out perfectly to 1. And this happens every single time as long as the two angles are the same. Like the theta in the formula has to be the same theta. So you can do mental math. Someone says, what's sine squared of 37 degrees plus cos squared of 37 degrees? You're going to say that it's equal to 1. That's big idea number 2. This is actually, we want to give this a name. Things that are always true in trigonometry, that's going to be our next unit after this one, are called identities. So this is the first identity that you've ever learned. That cos squared theta plus sine squared theta is equal to 1. It's on your formula sheet. On your formula sheet, and historically, the sine squared theta is written first. I don't know, it doesn't matter. But this formula will often be referred to as sine squared theta plus cos squared theta equals 1. And then if we go to our unit circle, and we did sine theta, we did cos theta, we ask ourselves, is something interesting happening with tan of theta? Tan of theta is the opposite side over the adjacent, so that would be my y value over my x value. And now, if your y value is sine of theta, and your x value is cos of theta, we have our big idea number 3. That tan of any angle is this identity, sine of theta over cos of theta. And we'll go back to our calculator here just to double check this. If I pick any angle, tan of 22 degrees, and push enter, And then I do a fraction with sine of 22 on top and cos of 22 on the bottom. According to the identity, I should get exactly the same answer, 0.404026. Do all the decimals match up?
Absolute.
This is big idea number 3. In this unit, if you're stuck on a question, sometimes one of these 3 big ideas helps you solve it. And all 3 of these big ideas are just connecting a circle to a triangle. Because if you pick any point along this circle with a radius of 1, right? If I pick this point right down here, I get a reference angle, I can go back to my nearest x-axis. I have an x-coordinate, I have a y-coordinate, I have the radius still 1. Using my reference angle, sine of theta is opposite over hypotenuse. Okay? And in fact, the unit circle also explains the cast rule that you had before. Like if I have this triangle and I do opposite over hypotenuse, can you see that your opposite side now is negative? Because it's going down. And in your cast rule, sine is negative in quadrant 3. Your x-coordinate is negative because it's going to the left. And if you do cos of theta in quadrant 3, it's negative. And tan is opposite over adjacent, but you have a negative value divided by a negative value, it becomes positive. So it's kind of neat to see that something like your cast rule, when you take it within the unit circle, actually makes sense. Why those things work. Right now, up till now, we probably just developed the cast rule by trying things in different quadrants and just saying, I noticed a pattern, therefore I have this rule, because the rule explains the pattern I saw. That's a good level of understanding. Now we've developed a deeper level of understanding, because we can see based on the coordinates and the unit circle, it has to be. If sine is your y-coordinate, can you see in quadrant 1 and 2 your y-coordinates are positive? But in quadrants 3 and 4 your y-coordinates are negative. Cos is your x-coordinate. Quadrant 1 and 4 your x-coordinate will be positive. But in 2 and 3 it'll be negative. So our cast rule can be explained by this as well. In addition to sine, cos, and tan, if you turn to the next page, we have 3 new trig functions that we're going to use. So there's 3 primary trig functions. Those are sine, cos, and tan. And there are 3 reciprocal trig functions where we flip things. So the reciprocal of cos theta is the secant ratio. So one thing that we can write here, beside this one, you can write that. Wow, that's yellow. Secant theta is the reciprocal of cos theta. And this is called the definition of secant. It's also an identity for relating secant to cos. And vice versa, you could write.
All international students, please head to the library with your things. That's all international students. Please head to the library with your things. Thank you.
And cos of theta is 1 over secant. The reciprocal of sine is the cosecant ratio, so we can write that cosecant of theta is 1 over sine of theta, and vice versa, that sine of theta is 1 over cosecant theta. And finally, tan of theta, cotangent of theta is 1 over tangent of theta, and tangent of theta is 1 over cos of theta, and using our big idea, if cotangent of theta is the reciprocal or the flip of tangent, and we already know that tangent of theta from our big idea is sine theta over cos theta, then cotangent of theta, the reciprocal, is the flip. Cotangent of theta is always cos theta over sine theta. So introducing 3 new trig ratios, and all they are reciprocals of previous ones you've already known. So these are the 3 big ideas of this unit. At any point on the unit circle, and we'll go back to it, any point on the unit circle can be labeled now with theta as cos theta comma sine theta. That's just based on drawing a triangle. Since the equation of the circle is just a squared plus b squared equals c squared, you now have a very important identity that cos squared of theta plus sine squared of theta is always equal to 1. And finally, that the tan ratio is exactly the same as sine theta over cos theta. All right, let's go to example 1.